In summary, we want to find lengths in a regular n-gon in order to, our goal, of course, is to find the area. Area formula is 1/2 the apothem times the perimeter. In that case, you need the apothem length, or you need a side length so that you can compute the perimeter, multiply times the apothem, but you may not be given each one of those pieces. So in order to figure out one of the other ones, it's possible that you can use the Pythagorean theorem, where we'd have 1/2 of our side length being squared. Why is it a half? Let me come back to one of these little problems right in here, right over here. Remember that whatever, this is the right triangle that we're dealing with, and this side length is half as big as the original side length. So yeah, 1/2 of the side length that's being squared times the, or plus the apothem squared is equal to the radius squared. Right, we could use that. I mean, that's assuming that they gave us any two of them. We're going to have special right triangles in some cases. We have a special right triangle when we have an equilateral triangle, a square, or a hexagon. There's a couple more. We're going to see those in the course of the lesson, or the course of your homework, or the challenge problems, or something like that. And then for everything else, you can just use trigonometry. Figure out what your central angle measurement is, cut it in half, and then you've got yourself a right triangle that you can perform some trig on. Sine, a cosine, or a tangent. Let's take a look at a couple of more problems here on example 5. Find the area of each regular polygon. And in each of these cases, 10, exactly the same, is the radius length of our shape. And we only have one piece. That's all you need. Just have one piece and we can figure out the rest of them. All right, and I'm going to anticipate, I don't need any extra space. Look at this, I did not include extra space in here. I'm going to just use what I have been allotted. All right, I am going to throw in my apothem length here. I'm also going to put in my central angle, maybe off to the side, 360 divided by 3 is 120. Cut that in half. I get my 60-degree angle right here, so there's my 30, 60, 90 right triangle. The radius of the triangle, or the radius of the equilateral triangle, is the hypotenuse here. If I cut that in half, I get 5 for the length of my short side, and then it's going to be 5 times the square root of 3 for the longer leg. But I'm going to need the whole entire side length, and the whole entire side length will just be double that. So that would be 10 times the square root of 3. Now I have enough information. I have a side length, I have the apothem length. I can put it together with our 1/2 the apothem, which is 5, times the perimeter. I've got 3, and each of these sides is 10 times the square root of 3. Now it's just a matter of multiplying all of this stuff. Simplifying, I'm going to take half of the 10. It's the only even one on here. Get 5. 5 times the other 5 is 25. 25 times the 3 gives me 75. Square root of 3 units squared. Boop. Why aren't any of these giving me units? I don't know. All right, so then we have a square. And we know that whenever we draw in, I may have to switch colors so we can actually see some stuff here. Boom, 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 boom. We draw an essential angle. 360 divided by 4 gives me 90 degrees. Cut that in half with the apothem there. Gives me 45. And then I have my 45, 45, 90 right triangle. Okay, so in order to find the length of our little side here and the apothem if I want to, so remember this is supposed to be x times the square root of 2, but there's no square root of 2 on there. So to find the length of this x piece that's down here, I'm going to have to divide 10 by the square root of 2 instead of multiply. So divided by the square root of 2, but then, you know, we don't like to leave square roots on the bottom, so we're going to rationalize it by multiplying by the square root of 2 over the square root of 2. And for some reason, I kept pink. Okay, whatever. And multiplying straight across, I get 10 times the square root of 2. And on the bottom, square root of 2 times square root of 2 is just 2, which can simplify to the 10 and the 2 can cancel and give me 5 square root of 2. So that's how big this piece is down here, 5 square root of 2. And then the whole entire side length then is going to be double that, which is 10 square root of 2. Now, I can either use the apothem, 1/2 the apothem times the perimeter, but if I've got a square and I just figured out the side length, come on, we're just going to use the formula for taking their side length which is 10 times the square root of 2, and then just squaring it. So when I square these two things that are being multiplied inside of the parentheses, I just square both of them. So 10 squared is 100, and then the square root of 2 squared is 2. So 100 times 2 is 200 units squared. Okay, let's look at example 3, where we have ourselves a hexagon. Can we go back to blue? I hope so. Let's draw in our apothem length. Not only that, how about another radius? 360 divided by 6 gives me 60. Cut that in half. 30, and there's my 30, 60, 90 right triangle. And this time I'm given the radius, which is the hypotenuse, again, is 10, which means that the shorter length down here is 5, and the length of the apothem, the longer leg, is 5 times the square root of 3. Once again, I have enough information in order to solve our area formula. 1/2 of the apothem, which is 5 times the square root of 3, times the perimeter. Well, I only have the little side length here. If I double that, I get 10. Remember, that's the same as the radius there, which means that 10 times 6 is 60. Why did I do a bracket and then a parenthesis? All right, and then maybe simplifying this, I can take half of the 60 and get 30. 30 times the 5 is 150. Yeah, so I got 150 square root of 3 units squared. All right, do we have more of these? We probably do. In example 6, find the area of each of these regular polygons. So again, I have a pentagon, but this pentagon has the radius of 10, kind of goes in with the other problems that we had here. And then we have an octagon. And instead of given the radius, we're given the side length. Okay, so let's see what we're going to have to do for each one of these. So that regular pentagon is going to be very similar to the one that we just did back here on example 4, where we had to break it down to the trig. And the reason why is because we only have one side length. We only have the radius length. So I'm going to repeat my process by bringing down an apothem. If I were to draw an essential angle and take 360 and divide it by 5, I get 72. Cut that in half, I get 36. Not a special right triangle, but it's okay. What two pieces of information do I need? I need 2 of them. I need the apothem, which I'll call A, and I'm going to need a side length down here. I'll just call that thing X. And I'm given the length of the hypotenuse. I'll actually label that as a hypotenuse. Let's find it a piece at a time. The A here is the adjacent side, and I'm going to use cosine. Cosine of 36, yeah, this is looking really familiar, is equal to my adjacent side over my hypotenuse side, which is 10. Just multiply the 10 over. My apothem is 10 times the cosine of 36. I wonder if you could develop a formula for this in terms of sines and cosines and stuff. Probably. All right, and then let's say I want to find the x. The x now is the opposite side over here, which is going to use sine. Sine of 36 is equal to the opposite side, which we're calling x, over my hypotenuse of 10. Multiply the 10 over, and I get my x side as 10 times the sine of 36. All right, and now our side length is double that. It's double this 10 times the sine of 36, which is going to make 20 times the sine of 36. All right, we have our side length, we have our apothem. We've got enough information to write the equation for the area. 1/2 of the apothem length, which we said was 10 times the cosine of 36, times my perimeter. Each one of these is 20 times the sine of 36. If I multiply that times 5, 5 times this 20 here gives me 100. 100 times the sine of 36. All right, and then maybe what I do to clean this thing up is change colors and take half of this 10 here and make that 5. 5 times 100 is 500 times the cosine of 36 times the sine of 36. And you can leave it like that. There's nothing wrong with that answer. It doesn't say that we had to get an approximate answer. If you wanted to get an approximate answer for that, it would be in your calculator, of course, as we had 500 times the cosine of 36 times the sine of 36. Whoa! Hey, there's the exact answer. Terms of square roots and stuff. 237.76? 237. Is that what I said? I probably didn't. 237.76 units squared. Lovely. All right, let's do one more. One more before the end of this video. Hopefully it doesn't last another 35 minutes. All right, we have ourselves a regular octagon, a stop sign. It's just a purple size stop sign. Maybe stop signs should be purple. I don't know, people would probably ignore them. They need to be red. All right, anyway, draw an essential angle. And so this is one that we haven't done before. It's going to be important to do this. It's 360 divided by 8. So 8 goes into 36 4 times with 4 left over. Yeah. And that would be 8 into 40 is 5. 45 degrees. So all of that right there is 45 degrees. But I need to split it in half. You split it in half if I bring in my apothem. And then I have 45 divided by 2. Doesn't go in there evenly. 22.5 degrees. Ah, oh, man, are you kidding me? 22.5 degrees. And I'm given the whole entire side length of 10, which means the little part of our right triangle here is half of that of 5. Now, this time I only need one piece of extra information, which is going to be our apothem length. And since it's not a special right triangle, and I don't have enough information to use a Pythagorean theorem, I'm going to have to use trig again. So let's figure out what sides we have. Directly opposite the 22.5, our 5 here is our opposite side. And the A is adjacent to our angle. O and A looks like a tangent. Tangent of 22.5 degrees is equal to my opposite side, 5, over my adjacent side, I don't even know. And this time my adjacent side is on the bottom, which means I'm going to have to flip those. I'm going to have to switch them out to get an apothem length of 5 over the tangent of 22.5 degrees. There's my apothem. Leave it like that. We're going to do all our mathematics in exact form, and then we can round it at the end if it's necessary. All right, our area is equal to 1/2 the apothem, which we just found as 5. What a crummy looking 5. 5 over the tangent of 22.5 times my perimeter. One side is 10. I got 8 of them. Pretty sure that's 80. Okay. All right, and then let's do some simplification. Take half of that and give 40. This is really like it's 40 over 1, and you do top times top and bottom times bottom to get an area of exactly, 200. 200 over the tangent of 22.5. Again, that would be okay if we are not asked for an approximation, but maybe it'll make you feel better if we put it into the calculator. 200 divided by the tangent of 22.5 degrees is 482.84. Units squared. And there you have it.